Hello, AP Chemistry students. This is sections 3.7 through 3.10. So I'm trying something a little bit different here. 3.7 through 3.10, they were all much lighter topics and they were all related. So I figured it would make more sense to combine them all into one video rather than making a single video for each. So 3.7 is on solutions and mixtures. 3.8 is on representations of solutions. 3.9 is on the separation of solutions and mixtures using chromatography. And 3.10 is on solubility. So as you can see here, it's all about solutions. So our learning objectives for this one are to calculate the number of solute particles, volume, or molarity of solutions, to use particulate models for mixtures to both represent interactions between components and represent concentrations of components, to explain the relationship between solubility of ionic and molecular compounds in aqueous and non-aqueous solvents and the intermolecular interactions between particles, and lastly, to understand how chromatography and distillation help separate components of a mixture based on intermolecular forces. So you probably know a bit about solutions and mixtures already, but sort of a technical definition of a solution, otherwise known as a homogeneous mixture, is any sort of mixture of substances that is the same throughout. So it can be a solid, liquid, or gas, but the macroscopic properties cannot vary throughout the sample. So what that means is that if you had some sort of mixture of solids, liquids, gases, any combination of those, that any small chunk of it that you remove is going to be the same as any other small chunk. The macroscopic properties, the say like the boiling point or the viscosity or the color, they're all going to be the same throughout. Otherwise, they're known as a heterogeneous mixture, which is not technically a solution. So in this diagram here, we have the homogeneous mixture or solution being represented as the green and purple circles being evenly distributed, whereas the heterogeneous mixture is the green stuff all shoved into one corner and the purple stuff kind of floating around it. A good example of a solution would be when you pour like milk into a coffee and then it all spreads out. Versus if you were to put ice cubes in a coffee to make iced coffee, that would be more of a heterogeneous mixture because the ice cubes are not going to be the same size. You're not going to have the same sort of a macroscopic property throughout it. So we talked a lot about this in section 1.1 at the very beginning of the school year, but the composition of a mixture is usually expressed in terms of molarity, which is a unit of concentration of the amount of solute per amount of solution, so the amount of things dissolved per amount of volume of the medium in which it's contained in. And this is usually measured in units of moles per liter. And a solution can have multiple solutes and therefore have multiple concentrations. So for example, if you had a 1 liter solution and you added 1 mole of sodium chloride and 2 moles of potassium fluoride, you'd end up with a solution that was 1 molar sodium chloride and 2 molar potassium fluoride. So the solution can have multiple different molarities depending on which solute that you're focusing on. And since since molarity is equal to the moles per liter, you can always solve for one of these variables if you know the other two. So if we know the molarity and the volume, we can calculate the moles. If we know the moles and the volume, we can calculate the molarity. Or if we know the molarity and the moles, we can figure out what volume that we need to get that amount of moles. So here's an example. How many moles of sodium chloride are in 700 milliliters of a 0.450 molar solution? So we know this is in moles per liter, so we need to turn our volume into liters. And conveniently, this is moles per liter. So if we multiply this molarity in moles per liter by the volume in liters, the liters are going to cancel out. We're going to be able to solve for the number of moles. And you can see that I did that here. The liters cancel out. 0.450 times 0.7 is going to be 0.315 moles of sodium chloride. And this is one of the most valuable things that you can have in chemistry, particularly when you're doing experiments with solutions. And sometimes on the AP test, you're going to be shown particle diagrams to represent solutions, and you need to know how to analyze them. So let's look at this one below. We have 4 different solutions. One's 0.2 molar potassium chloride. And we can see here that we have 1, 2, 3, 4 potassiums and 1, 2, 3, 4 chloride atoms. So this might not really mean anything in terms of 0.2, but we can use this as sort of a relative guide to compare to other solutions. So here we have a 0.1 molar potassium chloride solution, and you can see here we have half the number of particles. And that makes sense because the concentration of 0.2 molar should be double the concentration of 0.1 molar. Now, if we had 0.1 molar magnesium chloride, that's going to be sort of a different situation because in 1 unit of MgCl, there's 1 Mg and 2 Cls. So based off of the other 0.1 solution, we'd expect everything that's 1 in the formula to have two atoms being represented, which we do see here for the 2 magnesiums. And then since there are 2 chlorines per every 1 unit, we would expect double that for the chlorides. We can see that there are 4 here, and that makes sense. And here we have a 0.1 molar solution of hydrogen fluoride or hydrofluoric acid. You can see here that they are not dissociated. You don't really need to know anything about this yet. We'll talk about this later when it comes to acids and bases. But you can see here we still have the same relative number of particles being represented by the 0.1 molar solution. All right, so knowing if two substances are going to mix, if they're going to become a solution in the first place, or if two substances are miscible, which is a word to describe if they are soluble in each other, able to mix with each other, is it going to be entirely based on the intermolecular forces of the substances. And the more similar the forces are, the more likely they are to form a homogeneous mixture, aka a solution. So the sort of classic example of a thing that's not a solution is oil and water, because oil is nonpolar and it's going to be only London dispersion forces, whereas water is very, very polar with its hydrogen bonds. And these are dissimilar forces. So nonpolar things and polar things generally are not going to be able to mix very well because their intermolecular forces work very differently. So this phrase here, like dissolves like, is a pretty good guide for understanding this. And this table here kind of shows you a general idea of what's going to be able to dissolve in what in terms of polar and nonpolar substances. So ionic substances are going to be usually soluble in polar things because you can have ion dipole interactions, but generally non-soluble or insoluble in nonpolar substances. It's kind of hard to get salt to dissolve in oil, or not as easy to dissolve salt in oil as it is to dissolve salt in water. Polar substances are always going to be soluble in other polar substances. That's sort of the like dissolves like here. And generally, nonpolar and polar things are insoluble, not able to mix, kind of like the oil and water example. And sort of the opposite is true for nonpolar, and nonpolar stuff is soluble in itself, but not soluble in polar compounds or polar substances. So substances, even if they are soluble within each other, are not going to be infinitely soluble. For example, if you had a glass of water, you cannot infinitely add salt to it, even though ionic compounds are generally soluble in polar substances, because everything's going to have a bit of a solubility limit. And using the table salt example, its solubility limit is 357 grams per liter at 25 degrees Celsius. I don't know if you've ever done anything like this in cooking before, but or like if you were making some sort of baking or doing something where you're mixing like sugar and salt with liquids. Sometimes the hotter the liquid gets, the more soluble it is, the more kinetic energy the particles have with each other, the more they're able to break up and kind of mix with each other. So the solubility of a substance is always going to be based off of the temperature. And if you try to exceed this limit, you're going to end up with a situation where it starts to clump at the bottom. You start to get crystals at the bottom. And this is called a saturated solution. Once you've reached to the point where you can't dissolve anymore, your solution is considered to be saturated. There's also something called a super saturated solution. This is sort of a special case where you heat up a substance and get those particles moving more so that it can dissolve more, therefore getting a higher concentration of your solute in your solution. And then if you cool it down really slowly, sometimes that solid won't crystallize out and will remain in the solution. So it'll be a lot more concentrated than it technically is supposed to be able to. But the problem with that is it's sort of unstable. If you were to drop like a tiny little bit of salt into a supersaturated solution of sodium chloride, that would cause a lot of crystallization of the dissolved salt to then drop out of solution. All right. So speaking of solutions, solutions are generally hard to separate because they are so homogeneous. They're so like mixed in with each other. But there are some tricks, usually for analysis purposes, where you can separate out different substances in a mixture based off of their polarity and intermolecular forces. And a really common version of this is called chromatography. So chromatography is the separation of a mixture of substances by passing it through a solution with a medium in which the components of the solution move at different rates. So sometimes you'll have a mixture of substances that have similar properties, but if you pass that through some sort of medium that is like more extreme in one of those properties, one of those solutions might be more attracted to that medium than the other one, and then they'll sort of flow through that medium at different rates, causing those two substances to separate a little bit. So say you're using a polar solution, the more polar substances will be attracted to a polar medium, and the more nonpolar ones are going to get left behind. They're not going to be able to stick to the nonpolar medium as well. And the opposite is true if you're to use a nonpolar solution. The nonpolar things would be able to interact with it very well, and the polar things would not. So a good example of this is something called paper chromatography. And we're going to be doing a small lab on this, but the idea behind paper chromatography is that you use paper as a medium for what is called a mobile phase, which is a solvent being used to separate the substances, which is going to pass through the paper, which is called a stationary phase. So a good example of how you do this is if you were to take a piece of paper and put an ink spot on it. So usually black ink is made of multiple different colors of ink that are sort of combining to give you that black color. But those multiple dyes can actually be separated based off of their polarities. And this is going to be really similar to what we do in the lab. And we can dip this paper in water. And what's going to happen is the process of wicking. That's when you dip something in water and then the water starts to travel through it. So the paper is the stationary phase that the mobile phase is going to pass through, the mobile phase being the water. So then the water is going to travel up the paper. It's going to hit the ink spot, and the water is a polar solvent. So depending on the polarity of the dyes in the ink, the more polar dyes are going to be more attracted to the water than the more non-polar dyes. And you'll start to see a separation. You can see the black ink dot is starting to disappear, and then it's separating out into three different colors. And you can see here that the blue is traveling the fastest and the yellow is traveling the slowest. So that tells us that the polarity of the blue dye is more similar to the water that is wicking up the paper than the yellow dye is. And eventually they will become so separated because their rates are going to be so different, and the blue is eventually going to get ahead and the yellow is eventually going to get left behind. Now, it's going to be hard to do anything with these substances because they're going to be kind of stuck to the paper, but it at least gives us a good idea of the relative polarities and the relative intermolecular forces that are at play in the dyes within this mixture. Um, so I kind of already explained this. Let's see. Okay. So a way you can do analysis on this is by calculating something called a RF value, which stands for a retention or retardation factor. And this is a ratio where you calculate what the distance traveled by the solute is divided by the distance traveled by the solvent front. So the solvent front is referring to the distance traveled by the mobile phase. Like in the previous example, that would be the distance traveled by the water up the paper. You want to know, for example, how far the blue dye traveled relative to how far the water traveled. Because the closer to one that value is going to be, the closer in polarity the substance that you're analyzing is to the mobile phase. Um, so like say here, for example, our origin was here. So this is where our say our blue dye started, and our blue dye was able to travel 2.1 centimeters up the piece of paper, whereas the water, using the previous example as an example here, I was able to travel 2.8 centimeters. So if I want to know what the RF value is here, I'm going to divide the distance traveled by the solute, which was 2.1, by the distance traveled by the solvent front, aka the distance traveled by the mobile phase, which is 2.8, and we get a value of 0.75, which is telling us that the whatever this blue dot is pretty close in polarity to the mobile phase, but not quite the same. The closer that value is to 1, the more similar they are in polarity. And you can imagine that if we were looking at the yellow dye in the previous example, it would have a much smaller RF value. So another type of chromatography is called column chromatography. This one's a little bit better if you want to actually have an amount of the sample to work with and study afterwards. That's not just stuck to a piece of paper. And the way this works is it uses gravity rather than wicking. So in a column chromatograph or in a column chromatography experiment, you have some sort of tube that is packed with some sort of solid substance. This is our stationary phase in this case, but in this example, the stationary phase is actually the thing that has a certain polarity. And then you pour the solution, which we call the elutant in this type of experiment, and it'll start to drip through this solid stationary phase. Sometimes it's like beads of silica or something like that. It's some sort of substance that's going to prevent the liquid from draining really quickly, especially because the more the properties of that substance relate to the property of the solution, it's going to slow them down. It's kind of the opposite of the last example in the paper chromatography, where you're going to measure how similar they are by how fast they travel. This one, the more similar the properties of the solution are, or the properties of the substance within the solution are to the stationary phase, the slower they're going to travel. So we can see this example. We have some sort of purple liquid on top of the little beads in the column, and they start to drip through, and you see that the red is now getting ahead of the blue. And as time progresses, they get more and more separated because it seems like the blue part of the solution is more attracted to the beads in the column than the red part of the solution is. And eventually they separate out completely. We can collect the red once it gets ahead of the blue, and then take away this little beaker here, and then put another beaker there, and then collect the blue. And now we've successfully separated the red and the blue components of the solution. Another way to do a similar thing is called distillation. This is when you have a mixture and you separate out the substances by boiling them. Because say you had alcohol and water, they both have hydrogen bonds, so they're going to mix pretty well in each other. It's going to be hard to separate them. But if you look at the boiling points of water and alcohol, water boils at 100 degrees Celsius, whereas alcohol boils at around 80 degrees Celsius. So what you can do is you could take your solution, in this case, an example of water and alcohol, and start to take it up to 80 degrees Celsius, which is going to be the boiling point of the alcohol, but it's not going to be enough energy to boil all of the water. So you can see in this setup here, we have a flame that is heating the solution. It's going to become gas. Once the alcohol boils, it's going to become gas, and it's going to travel down this tube. And this usually has some sort of cooling device using water so that the alcohol in the gas phase can then start to condense. And then as it condenses, it'll drip into another container, and you can collect it that way while the water itself is still boiling. And then you can remove this, much like we did in the column chromatography example, and then bring up the temperature, and then you could separate out any other parts of the solution if they have, say, like higher boiling points. And like I said before, this is going to be all based off of intermolecular forces. The stronger the forces, the higher the boiling points. So the only way to really separate things in a mixture is to sort of play with those intermolecular forces and the subtle differences between them. So that'll be the end of this video, and I'll see you in 3.11.